Today we're going to look at the flip-flops that I've got in this IC package. So I went ahead and highlighted some of them. There might actually be a couple more in here that I missed. I went ahead and looked up all of the data sheets for each of them. I printed out some of the important pages, and we're going to start to go through those today. Most of them are going to be the same, or they're going to be at least functionally the same. Sometimes the pins might be a little bit different, or they might have some weird little thing that's different on them. For example, there might be a positive edge versus a negative edge on the trigger. And we're also going to take a look at what flip-flops were originally used for, or at least these types of flip-flops. And we're going to explore a little bit on a sample circuit on a breadboard. It won't be anything too complicated, and it won't be anything that's going to just be super exciting that you're going to rush out and want to get yourself a whole bag of flip-flops. The first one I pulled out is going to be this surface mount one, and this is the 74ABT821D from Philips, and it's a 10-bit flip-flop positive edge trigger. Now, I don't really have any convenient way of testing a surface mount component like this, and I'm not going to bother to try. I've got a bunch of other flip-flops that are all going to do the exact same thing that are in DIP package. But anyway, here's one option, one of our flip-flops. And here's another flip-flop. This one is, and I don't know who the manufacturer is, it's just a big giant S. So if you know who that is, you can leave a comment down in the comment section below. But this one is a 74ALS373N, which I think is probably pretty common. If you look at the sides of this one, you can kind of see it looks like they've been tinned a little bit. So again, I think this one might have been pulled as opposed to in a socket. What they do is if they pull them out, they'll straighten the leads and then they'll kind of dip them in a pool of solder, which will create a real nice little clean look, and they kind of look like they're original, but if you know what to look for, they're really not. But anyway, this one here is another flip-flop. This one just says latch a flip-flop, and I think the data sheet was a little bit minimal, but we'll take a look at this one. This one I did put in a breadboard, so we'll go ahead and take a look at that as a circuit. Here's another flip-flop. This one is the CD74HC377E from RCA. And this one's a nice little ceramic package. I think it's from 74. It's got a date code of 741, which I think is the first month of 1974. So this one's definitely getting up there in age. I've got the data sheet for this one. We'll go ahead and take a look at that as well. And it also looks like it might have been pulled from an existing circuit. And another one, this one's marked Japan, and it's got a real interesting little logo here. I'm not sure what it is. I don't recognize it at all. And this one is the HD74LS374P. And this is a D-type edge-triggered flip-flop. And I've got the data sheet for this one as well. But like I said, these are all pretty much the same. They have some slight variations, but in general, they all operate about the same. So let's slide these trays out of the way so we don't knock them over, and I'll grab a couple flip-flops and a breadboard and some of those data sheets. So before we get started, let's take a quick look at how a flip-flop would have worked on an old 8-bit-ish computer. Now these are all 8-bit. Actually, I think one of them might have been 7 bits. But these are all 8-bit, and the 8-bit refers to the data bus. And what would happen is there would be 8 bits that would get sent out, essentially 8 different lines. There would be 8 different tracks going through. And then the different peripherals, so the memory, the display, the CPU, would all have connections to that bus. And so when they wanted something, they can say, hey, I want to get such and such piece of memory from the memory, and I want you to put it on the bus so that I can read that. And the way they would do that is using something like a flip-flop buffer. And the reason they did that is because you've got all these guys sitting on the data bus, and they needed to know which piece of data was theirs. And they also didn't want to be delayed. So if they put a piece of data out, they wanted to be able to assume that that data was going to get there or be retrieved or be sent in reliably. And so these flip-flops would put the data in and then store the pieces of information and then be able to reliably pull that out even if the timing wasn't perfect. The other interesting thing about these flip-flops is that because you had all these guys sitting on the bus, you needed to make sure that there wasn't a high impedance such that you would pull that data bus down. So all these flip-flops that we're going to take a look at all had high impedance, so meaning that if you were just sitting there with data, or if you were just sitting there and you weren't using the buffer, it wouldn't cause any drain on the voltage supply of the data bus, and you wouldn't negatively impact anybody else using that data bus. Because remember, this data bus was actually shared by all the peripherals. Now, of course, a lot of this is done completely different today, and there's all kinds of great videos and YouTubes out there about how these 8-bit computers worked and how you can set them up and learn all about them. But today we're just going to look at these flip-flops that were in here for transmitting data back and forth between the peripherals and the data bus itself. Today we're going to look at this one on the breadboard, and I'm going to talk about the differences on some of the other ones, but I went ahead and printed out just a couple pages of the actual data sheet so we can walk through that real quick. Let's zoom down a little bit. So this is the one we've got. We've got the 737, and it's very similar to the 734, especially on the pinouts. In fact, I think the only difference is they were just physically labeled a little bit different, but the functionality was the same. So this is the one that we've got, and we're going to go through all of these pins here in just a second. So here's the logic diagram. We're going to take a quick look at that first. These ones are going to be 8 in parallel because this is an 8-bit flip-flop, which means there's 8 of them, and it can then take into consideration one piece of data for each in order to make up the 8 bits. Now on the top, we've got the data line, so D0 through D7, and those are going to be what pushes the data in. Now once it goes into the flip-flop, it's going to based on this enable chip here, or the CP, depending on which version it says. And this is going to, if this is on, then it will accept the piece of data coming in. And keep in mind, these are just single ones or zeros that are coming in. So if this is enabled via a clock cycle, then the data values along these 8 bits will then get loaded into this flip-flop. And once they're loaded in, they're going to be stored. Now, it's going to only latch that data in when this data bus goes high again. And that's where you see the different latching types. So when this goes high, then this data that's on D0 through 7 will essentially be copied into the flip-flop. And once it's in there, it can't be overwritten or replaced. You can go ahead and change the data pins coming in. It won't have any impact until you actually flip that clock cycle again. And we'll take a quick look at that here when we wire this up. Separately, this has got an output, and this is active low, so this is the output enable, and this allows you to pull the data out. So until this goes low, so if this is normally high, and when this line gets pulled low, then the data is now available on the output, and that's going to be Q0 through Q7, and they're all going to correspond appropriately. Now you can take this low and low and high multiple times, and you'll get the same data out every single time until that data is replaced. And again, until you latch in new data, anything that's positive or negative on this line here won't make any difference. So you can think about it as it pushes data in, and then latches it, copies the data into the flip-flop, and then it can be pulled back out and then redo the whole process again with a new set of data. Now, that may seem super, super slow, but these can operate at an extremely high rate of clock cycles. And I did put some up on the oscilloscope just to take a look to see, using an Arduino, kind of how fast it is and if it would ever lose track. And the fastest I could get my Arduino clock was about 4 megahertz. And it had, honestly, it didn't look like it was having any problems, but there wasn't a good, easy way to tell. And we might take a quick look at that as well. And then here's our functional table, and we're not going to go through this in great detail, but the bottom line is what I just said. Based on the input enable, which is our E pin, which is our clock pin, when it goes high, we'll then load the data from the register, from the D pins into the internal register. And then when that goes low, it doesn't matter if that input changes at all. It has no impact. And it will stay in this internal register until the next clock cycle and we push a new piece of data in. Likewise, the output enable, that's going to be low. And then when that goes, or I'm sorry, it's going to be high. And then when that goes low, that data from the internal register is now going to be available. Again, low, low, high, high, and so on. It doesn't change the data. Now, there are some flip-flops that might, but in this particular case, they're not. So whatever goes in is going to come back out. We'll take a quick look at the pinout. This is the one we have, the 373. The 374 is the same. It's just has some things labeled a little bit different, but functionally, they appear to be interchangeable, at least from a pin standpoint. So on the top number 1 pin here is our output enable. All the way down here on the pin 11, the lower right, is going to be our data in enable or a clock cycle. And then these are a little bit, I wouldn't say random, but I mean, we've got data out, data in for the first one, and then data in, data out for the second one. And so they're kind of all intertwined and flip-flopped here. I'm sure there's a reason based on the die as to why they're laid out that way with the footprint, but it's pretty straightforward. The D's are the inputs and the Q's are the outputs. And then I mentioned that they're super fast, and so you can see the typical response or propagation delay, I should say, is 6 nanoseconds. So as long as you pull that high and then take it low again, you've got essentially 6 nanoseconds that data will be latched in. Anything less than that, and it might not be latched in. And then for some reason this one's measured, this is the 374, for some reason that's measuring it in megahertz instead of the propagation delay, and that says 50 megahertz, so extremely fast. Not in today's standard, but definitely for some of the 8-bit computers. And this is that Motorola one. You can see it's almost identical. In fact, the pins are the same and the truth table is the same. And you can see down here that the circuit diagram is the same. They drew theirs slightly different, but the effect is the same. They've got their clock line a little bit higher, but it's functioning exactly the same as the other one. And here's the 74HC240 one that I have. This one's a little tiny bit different than the last two that I looked at, but it also is an 8-bit. Now this says inverting buffer with 3-stage outputs. This can be used as 2 4-bit buffers or 1 8-bit buffer. So this was probably in that transition time where there still were 4-bit data buses out there, but you could use them as both simply by tying the data lines and the output lines together, or not the data lines, the clock lines and the data lines together. You could turn both halves on and off at the exact same time or treat them separate. And so here's the functional diagram. You can see it's just a little tiny bit different. It has 2 segments, 2 4-bits, but it functions about the same. We've still got the same clock line coming in. We've still got the same output line coming in. We still have 4 data lines coming in and 4 data lines coming out. And this one mentioned that it was inverting, and so you can see that here where the input, if it's low, it's going to come out high. This is the Texas Instrument, the CD54HC377. And again, this one's pretty much the same as the first two. It's octal, which is 8 D-type flip-flops with a buffered clock, just like we saw before. And you can see the pin outs are the same, and this is pretty common with these packages. That way they were all largely interchangeable from a pin standpoint. So then you really only need to worry about the functional logic. So you can see it's got a little bit of a different logical diagram. They've got a bunch of logic here at the top. I don't know if this functionally is different than the others or if the others just simply didn't have that on the data sheet, but it does work kind of the same. It's got the clock cycle down here, and this is the enable up here. And here's one more, another octal D-type edge trigger. Now that's different than the others that we saw flip-flop. And again, it's going to be pretty much the same, and the pinout appears to be the same. And this one's got a combination of the diagram as well as the pinouts, which is actually kind of handy when you're just looking at it. And it's got the clock on number 11, and then we've got the output control up at number 1. And this is the last one. It's the SN54LS112. And this one's a little bit different than all of the others, and I'm not sure exactly what this one is used for. This is a negative edge trigger, and it's a dual JK flip-flop. Now, this one does have something called a preset and a clear, and these are 2 different circuits that are internally that can be controlled separate. Now, I think these are a little bit more of just a flip-flop where you wanted to set it, and then if you want to leave it as a set and then eventually reset that through a separate trigger, you can. And I might put this one out on the breadboard separately and take a quick look at that as well, since it's a little bit different, since it doesn't appear as though it's really designed to work off of a bus. Well, for one, it doesn't have 8 bits, so it wouldn't work unless you had 4 of them. But I'm pretty sure this one had some slightly different purposes for a flip-flop. Here it is on a breadboard, and it may seem like a big mangled mess, but we'll go through it, and it's honestly not that complicated. So what I've got here is I've got the chip, and up in the top left, or I guess bottom left, corner is going to be pin 1, and then that's going to go down and then back up again, and we'll cover a couple of those, but I'm not going to go through each and every one of them. Now, in order to keep things relatively simple, I'm only using 2 data lines, and that's going to be this black wire and this white wire. And then I have my 2 outputs, which are my 2 LEDs, and I just currently have 2 blue LEDs, and if you look at the side, you can see I've got a resistor on each of their legs so that it doesn't draw too much current. Now on the chip, you'll see this orange line right here, which is in pin 1. This is our data output enable. Now I just currently have that tied low, and if you remember from the data sheet, tied low means output's on. Now normally you wouldn't have this just straight tied low, but we'll see where that comes into effect here in a few minutes. And then next to that, we've got our output. This is Q1's output. And then next to that, we've got Q1 data. And then we've got it's actually technically 0, but Q0 data. And this is Q1's data, or the second data line. And then this is the output for the Q2, or the second data channel. Now you'll notice these two, and we saw this on the diagram as well. So it's got the 2 inputs next to each other, and then it's got the 2 outputs on the outside. And that's repeated on the next set as well. For simplicity, I'm just going to use these 2, because if I put in all 8 bits, it would be very hard to see. And then I also wouldn't really have enough room for all of my switches as well. So going down, this is just our ground for our chip. And then over here in pin 11, this is our clock pin. And so this is going to be what clocks in our data. And then this is just our 5 volts for our chip itself, because it needs 5 volts to operate. Now I have 3 buttons. I have 2 data line buttons, and this one right here is my clock button up on the top right side. So this is going to be our clock. So I'm going to simulate the clock going in. And keep in mind, this could run in the kilohertz or megahertz range. So it can go super, super fast, and this chip can handle that. We're just going to clock things in at a normal human visible speed. So well within data spec. And honestly, things like contact bounce is not going to have any impact on this, just because we're going to be doing this in a very simple 1 bit at a time. Now on the bottom, this switch on the left is my data 1 switch, and this one is my data 2, or Q0, Q1, or D0, D1, as they're actually labeled on the data sheet. Now this one's going to be off is up, and then down is on. So that's going to be off, on, off, on. And then the same is true for the bottom one. Now the way this works is I'm going to clock in. So I'm going to go ahead and say I want to load this first LED in. So I'm going to put that as a 1. So I'm going to hold that down, and now I'm going to clock that in. Now when that goes down and it goes high, that's going to be what, well, it's going to let it in. But then when it's let up, when it goes low, whatever the state is on that low is going to get what's going to get latched in. That's the difference between the positive and the negative edge on the different data sheets. Again, for our purpose, it's not that relevant. But now, as long as I can do anything I want on these switches here, they're having no impact. Again, this is my data line. Now that I've latched that in, that's going to stay there until something else gets read in on the next clock cycle. So assuming I don't do another clock cycle, this will always be 1, 0, or on, off. And again, the data lines, my battery pack just went out. And it went out for good. Let me go switch it. All right, new battery pack. We're good now. So this is where I left it, with a 1 in the first position and a 0 in the second position. And again, these have no impact. Now, if I come along and I want to load in a new value, so maybe I want to load in a 0 and a 1, so I can then hold this one down, and then I can latch in the next one, the next clock cycle. Now you'll notice this one went out because it was 0, and this one lit up because it was 1. Now again, it doesn't matter. I can click these as many times as I want, and no new data is going to come in. This will be on the output until I latch in a new stream of data for those switches. Now you remember this data out here, this enable pin, and this was active low. So it's active when it's on ground. So if I were to remove that, you're going to see the lights go out. Now that does not mean our data is out. That just means our chip is not sending the signal out. So if I was reading on this buffer, but that wasn't my data, it wasn't my turn yet, I wouldn't get any data coming out of this chip. Now with this out, I'm going to clock in a new one. So I had 0, 1. So I'm going to put a 1, 0, so the opposite. So I'm going to hold this down. I'm going to clock that in. Now I should have, this should be 1 and 0, the opposite of what I had. So now if I want this data, I can go ahead and take that low, and now it presents that data out to me on the bus. And again, it won't matter if something else changes, if new data happen to be clicked, until we actually bring this high, or sorry, low, then that data is not presented to the data bus. And until we get a new clock cycle, no new data is going to get loaded in. So anyway, that's a quick overview of how the flip-flop with the buffer works. Well, there you have it. There's a simple breadboard of a D-type flip-flop buffer. And in this particular case, we're using this chip here. But as you saw from the datasheet, almost all of them did the same thing, or at least had the same pinout. Some of the timing might have been a little bit different, but functionally they would have done the same thing. Doesn't necessarily mean they're interchangeable, but it does mean that at least functionally for what we're doing, we would have gotten the same output. Now, a couple things to mention. I've been racking my brain for a long time as to what would be a practical use for a D-type flip-flop today in 2020, when we've got microcontrollers that can do pretty much anything that you would want, and obviously can store data and put data out on the bus. And even just as an auxiliary, some of the other logic chips, the 74 series, still can come into play today, but I can't really think of any good use for a 8-bit flip-flop. So if you have any ideas, post them in the comments below. I'd love to hear them, but shy of loading data in and out of a peripheral onto a data bus, I really can't think of any good use for one of these flip-flops. Now you might even think, well, a standard flip-flop would be helpful, but this is based on a clock and it's got 8 of them that are all tied to the same clock. Even just using it as a standard flip-flop to turn something on and leave it on and then turn it off on the reset really isn't practical in a circuit, and these things wouldn't be low enough power that you would want to do that anyway. But anyway, it was a lot of fun to learn about the D-type flip-flop, and I did put it on the scope and just get an idea of it. There was nothing super interesting on it. As high as I could go, which was 4 megahertz. It was able to keep up just fine, and it was just interesting to see, but it wasn't really interesting enough to do an explanation on. It did exactly as it said it was going to do. So anyway, until we see again on the next IC, if you have any questions, leave them in the comments below. And if you have any suggestions on what you might be able to do with a D-type flip-flop today, I would love to hear from you.